guys, I am super excited to teach you about slope fields and Euler's method. This is some fun stuff in our chapter on differentials, okay? So, all right, let's check this out. This is telling us about slope fields are a graphical representation of a set of slopes attained from a differential equation. So a differential equation is an equation that involves a derivative. That derivative represents all the slopes of a function. So it says in last time's lesson, we learned about solving differential equations by separating the variables. But even if you can't separate the variables, you can still use a differential to plot the slopes. Okay, so check this out, all right? We have this equation, this differential. And it wants me to find the slopes at each of the following points. Well, the slope at 3, 2, remember this is my x coordinate, this is my y coordinate, okay? The slope at 3, 2 would be negative the x coordinate over the y coordinate. The slope at the point 1, 3 would be negative 1 over 3, or 1/3. The slope at negative 2, 1 would be negative 2, so that's positive, over negative 1 or negative 2. Okay, so I can get all these different slope fields. This will be, or slopes, sorry. This will be negative 2 over negative 2, which would be a slope of 1. Now, this is a good question. Why can't you find a slope when y is 0? So let's say like it's the point, I don't know, x is 5, y is 0. Do you guys see there will be negative 5 over 0, which is undefined? So anytime y is 0, that's going to be undefined. All right? Okay, so this is now telling me to find and plot the slopes given for each remaining dot in the plane at the right. Okay, so this is negative x over y. All right, let me write that up here actually, just so I can see it and then zoom in a little bit. Okay, so this is a slope field, all right? The remaining ones. Okay, so let's talk about this real quick. Do you guys see how there's nothing here? Well, because on the x-axis is the line where y equals 0, and we saw that when y equals 0, these slopes were all undefined. Now, I like looking at the axes first when I'm doing this. Let's take a look at the x-axis. What can you know about the slopes on the y-axis when x is 0, okay? I need to slow down because I'm saying my words wrong. The y-axis is when x is 0. So no matter what, like let's take this point right here, right guys? That's the point 0, 1. 0, 1. And the slope field for that would be, 0. Let's do that point. That's the point 0, 2. The slope for that would be 0. What about the point 0, 3? Well, the slope for that would be 0. In fact, the slope of anything on the axis would be 0, except for that. That can't be because it's 0 over 0, right? So we don't have that one. Okay? Okay, cool. Let's do a couple more slopes here. I think I'll maybe go one quadrant at a time, I guess. This is the point 1, 2, 1, 3, 2, 2, and 3, 3. This is just going to help me keep track of stuff a little bit better. Okay? So in quadrant 1, okay, 1, 3 would be negative. So it's negative x over y. So it's negative 1/3. That's a downward facing slope, but not too steep. That's negative 1/2. That's downward and a little steeper. That's negative 1. So that's a 45-degree like downward slope. And that's also negative 1. So you'll notice everything through here is at like a negative 1. Does that make sense that that and that would be a negative 1? I like to look for patterns because then it'll make things a little bit quicker for me. Okay, so those are all negative 1. That's cool, and I'm done with the first quadrant. Okay, let's look at the second quadrant. This is the point negative 1, 1, negative 2, 1, negative 3, 1. It's negative x over y. So that would be a slope of positive 1, positive 2, positive 3. Getting a little bit steeper. Okay? And this was negative 3, negative 3. So that's the slope, negative 3 over negative, so negative. That doesn't make sense. Oh, it's because it's the point negative 3, 3, Mitchell, duh. Okay, so it's negative 3 over 3, which is a slope of 1. Okay, you can kind of see what this is making. A really cool slope field here. I don't want to change colors. Okay, let's go into quadrant 3. This is the point -3, -1. This is the point -1, -2, -1, -3. Okay, negative x over y, that'd be a -3 slope. Pretty steep negative. That would be a slope of -1, -2, -1/2, and -1/3. All right, cool. And then my last one here, my goodness, this is 2, -1, 2, -2, 3, -1, 3, -2, 3, -3. Okay, so it's -2 over -1. So it's a slope of 2. That's a slope of 1. That's a slope of 3, very steep. It's a slope of 1.5. That's a slope of 1. Really, when they're grading like slope fields on the AP test, they're looking if you're putting it at 0, undefined, positive, negative. That's about it. Okay, that's about it. Okay, something cool I want to show you guys. Let me pause this to get ready. Okay, so this is kind of cool. This is I just Googled Desmos slope field generator. So somebody like programmed this. You can see all these points. It's kind of fun. And there's our like movable point and what that does. Okay, so anyway, crazy program. But like it will put slope fields for me on here, which is kind of fun. So the one we just did was -x over y. And can you guys see that that's kind of looks like almost circular, right? And if I move this point around, let's see where I have to go to move that. Let's open this up. Okay, as it moves, you can see it moving. All right, let's go. You can see the point like changing slope as it goes. Just kind of, this is changing just on the b-axis up and down. I wonder if we can change them both at the same time. There you go. All right, and so you can kind of see how this like slope changes as we move it around. Okay, I don't know, kind of interesting. I like that. All right. Okay. So it says, in example 2, you made what's known as a slope field starting at the point 0, 1. Follow the flow of the lines to sketch the solution curve. Okay, so the point 0, 1. So a lot of times what they'll do is they'll give you a point over 0, up 1. All right. Okay, now, so I'm going to go ahead and make this one in red just so you can see it. My solution curve, so it kind of follows this. So what's happening is like, think about like you're a car, right? You're driving and you can't drive through there. It's kind of directing traffic. It's telling you to go like there. And then that's it. So then you go down there. Okay? You guys can see that? It's like a rough sketch. But here's the thing. We also know we have undefined slopes all along the axis, and I can't cross that. You know, you might be tempted to be like, oh, look, wee, a circle. Okay, it's actually not true because I can't cross where it's undefined because I don't know what happens. So I can go to there and I can go to there, but I kind of have to stop there. Okay, so follow the flow of the slopes to sketch a solution curve. Your graph is parallel to the slope lines and like an average of slopes. So wherever I give you a point, let's say I start over here, you're just gonna like follow your way through. All right. It's very like, it's not very like exact or anything. You're just kind of sketching that out. Okay. This is really important. Your solution curve must represent a function whose domain is the largest possible open interval containing the point. Okay. So let's check out doing the solution curve through -1, 1. So that's like right here. Okay. -1, 1. So let's follow that around. So that was 0. And then that goes down. And it stops here because I don't know what else to do. And on the other side, and it stops here. All right, so that's like my solution curve for that. Let's see. Sketch a solution curve passing through that and one passing through 0, -3. Okay, so over here, I'm like following the flow to there. Oh, that was fun. And then I'm kind of following the flow to there. All right, but again, it's like it's stopping. What type of graph does this differential equation seem to be producing? I mean, it looks like it's a bunch of circles or actually really semicircles. Okay, Oh, good. I was going to say, let's solve this differential. We are going to solve that differential in a minute. But it looks like it's producing semicircles. Now, why semicircles and not circles? We'll talk about that in a minute. So right here, this is a very, very important note. The most common student error in sketching a particular solution is to sketch too far and create a graph which is not a function. You have to set boundaries, right? So look, like I said, a common thing would be to go, oh, it goes around like that. Well, number one, that's not a function because it doesn't pass the vertical line test. But also, it crosses through the boundaries. So it says, why is the x-axis a boundary for the differential equation? Because the derivative is undefined on the x-axis when y equals 0. Okay? So it made these semicircles. Now, why semicircles? So I was going to say, hey, let's solve this differential. Hey, let's go. Let's solve this differential. You got this question right here. Okay, I'm going to bring the y up there. So it's y dy. I'm going to bring the dx up there. So it's negative x dx. So I have the integral of y is y squared over 2. The integral of negative x is negative x squared over 2 plus c. All right? Now, that's solving the differential. I haven't solved for y yet. I'll do that in just a minute. But let's find the particular solution for the differential equation who passes through the point 0, 1. Okay, so check this out. If y is 1, okay, 1/2 is 0 plus c. c is 1/2. Okay, so I get y squared over 2 equals negative x squared over 2 plus 1 over 2. First, I'm going to multiply everything by 2. That's easy enough to do. And then I'm going to square root both sides. So I get plus or minus the square root of negative x squared plus 1. Okay? Plus or minus the square root of negative x squared plus 1. And how do I decide whether I pick the plus or minus? Well, we use this point one more time. We say, okay, if I plug in 0, I want it to equal 1. Well, the square root of 1 is 1, so I'm going to pick the positive. So this one is the positive differential equation, negative x squared plus 1. Okay, so I want to show you guys something. Let's go back to this slope field calculator guide. All right, nope, there we go. And it was negative y over x. So there's my slope field calculator. Now I'm going to make this point. It's going to be the point, shoot, what was it? 0, 1. Okay, so this is going to be the point where a is 0, b is 1. That point right there, okay? Zoom in on this a little bit, maybe. Okay, cool. Now, I'm going to go ahead and write this equation that I just found, this differential, which was the positive square root of negative x squared plus 1. I forgot to put my equals. Check this out, guys. This is so cool. Look at that. Look at that differential equation. Now, it's a semicircle because I had to pick positive or negative, but check it out. Right? We go down to here. We go down to here. We put it on an open interval. So, because again, remember the slopes aren't defined right there. So those would actually be open circles. Okay? I could change that. But yeah, that's good. All right, now check it out. Find the particular solution if it's through the point 0, negative 3. Okay, well, first of all, I was going to say, oh, let's just figure out what the sign is. I actually do have to redo all this. Starting from, yeah, well, kind of all of it. Okay, so the point 0, 3, if I start up here, I'm going to this equation so you guys can see it. Okay, I'm going to that equation right there. If x is 0, y is 3. So, let me do it in a different color. All right, 3 squared over 2 is negative 0 over 2 plus c. So this time c is 9/2, so that's the first thing that's different. So then y squared over 2 is negative x squared over 2 plus 9 over 2. When I multiply everything by 2, y squared is negative x squared plus 9. When I square it both sides, y is plus or minus the square root of negative x squared plus 9. And I have to check one more time now on the point 0, negative 3. Well, if I put in 0, I get the square root of 9 And to make sure that that equals -3, I would have to pick the -1. So the answer for part B is negative square root of -x squared plus 9. Okay? So my point was the point 0, -3. So let's change this to the point 0, -3. Okay, let's turn off that differential. And let's turn on this one. And it's going to be y equals square root of -x squared plus 9. But that's not right. That doesn't go through that point because we had to choose the negative on this one. And so now it's a negative semicircle. Okay. So we're kind of like following my slope field through there. And it's kind of cool if you guys watch this. As I go around, it kind of follows my slope field. Okay? So that's called a particular solution. So that's pretty neat. That's why I make semicircles, because it's plus or minus square root. And a plus or minus square root is where semicircles come from. All right? Sweet. That was fun. Oh, shoot. I don't know what that was. Okay, cool. We're still recording, though, so we're good. Okay, for the differential equation, draw a slope field to the right. You guys might be looking at this and like, dude, that's so many points. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. That's 21 points. That's 42 points. I have to do 42 slopes. This is going to take forever. Okay, now, check it out. Do you see that it only matters what the y-coordinate is? It doesn't matter what the x-coordinate is because it's all defined in terms of y. So I'm going to like kind of be smart about this. So the differential is 1 over y. Okay. This whole row right here, y is 1, right? It's like the point 1, 1, 2, 1, 3, 1. Wait. Nope. I have to think sometimes, you guys. That whole point is 1, right? Okay, x is 1, 1, 2, 1, 3, 1. Yeah, that whole row is 1. So on that whole row, y prime is going to be 1 over 1, and it doesn't matter what the x is. So I'm making slopes of 1. These should come up at like a 45-degree angle. Okay? On this whole row, the y is 2, so y prime is 1/2. So those are a little bit like flatter, I guess, all the way through there. All right, up here, y is 3, so y prime is 1/3, so it's like a tiny bit even flatter than that. Okay, cool, cool. All right, let's move down here. What about 0? It's 1 over 0. It's undefined all the way through there. Completely undefined because I can't do 1 over 0. Okay, this is going to be, so y prime is 1 over -1. So these are negative slopes. This is 1 over -2, so it's -1/2 slopes. And then 1 over -3, so it's -1/3 slopes. Okay? So do you guys, can you kind of see this? Like I can kind of see it already. It kind of is like doing like something like that, huh? All right? But don't forget, I'm actually going to put this back here so I don't forget. Those are all undefined. So there's my slope field. So that wasn't as bad because I could like use it. Okay, y prime equals 1 over y. Let's go into this. And let's change, okay, let me get rid of that and that. Let's change this to 1 over y. It's not negative. Okay? So you guys see that slope field there? Okay. All right, cool. So that's my slope field. That's what that looks like. Draw the slope field in the draw. Okay, I did that. Graph the particular solutions passing through the points. -2, -1. That's right here. So when I draw that, it's going to be like this. It's going to be like, kind of, sort of. Okay. And then what about the slope field through the point +2, +2? So that one's going to look like, I should use a different color, not blue. I feel like that's going to go like that. Okay? So that's the particular solution. Now let's solve it for both of those. I'm going to solve it for the point -2, -1. and for the point 2, 2, and see if my equation actually looks like. What does this look like, guys? To me, it looks like a parabola on its side, which is usually a square root, like y equals square root x. Let's see. All right. Let's do this one first. My differential is 1 over y. I'm going to go ahead and change that to a dy dx. The y goes up there, and then that's 1 dx. So when I integrate this, I get y squared over 2 equals x plus a constant. All right? You can plug in these points at this point. You know what? I don't want this 2 right here. I'm going to multiply by the 2 right now. Y squared equals x plus 2 times the constant, but that's just a new constant. So that's okay. That was like constant 1, constant 2. But it's just much easier to plug in here. So this is what I'm going to use. All right, so at this point, I plug in the point -2. -2 plus a constant is -1 squared. So 1 is -2 plus a constant. So the constant is 3. Okay, so from here, it's y squared equals x plus 3. I square root both sides. Y is the plus or minus square root of x plus 3. And in order to get a -1, when I plug in a -2, I have to pick the negative. All right? So let's go to my slope field and let's graph that. Well, actually, I'm just going to graph it on here because you guys know what that looks like. It's an upside down square root that's left 3. Is that basically what I did? I graphed like an upside down square root that's left 3. That's like exactly what I graphed. Now for this one, I can go from this point right here. We have a constant there. Okay, so for this one, I'm going to go, all right, y squared is x plus my constant. So 2 squared is 2 plus a constant, so the constant is 2. So y squared is x plus 2. When I square root both sides, it's plus or minus the square root of x plus 2. And since y is a positive number, I'm picking the positive one. And then that's a positive square root that's moved to the, see, is 2. Why, that should be moved to the left 2. What did I do wrong? Did I just draw that super weird? This should have been moved over to. From that point, maybe I drew it super weird. I don't know, maybe it comes down like that. That's kind of what it shows me, I guess. I guess I was like, it's kind of hard with get these slope fields perfect, but there you go. Okay, so it's to the left 2, x plus 2. Let me get my slope field. All right, awesome. Hopefully you guys are okay with that. Okay, let's go ahead and do example 6 and 7, and then we're going to tackle Euler's method. Which of the differentials snatches the slope field? Okay, here's what I like to do. Okay, this looks like, so when I look at this, like I'm going to look at a whole row or a whole column. Does that look like the slope is 1? Like to me, it kind of looks like positive 1. And that's going to mean, it's on the x-axis, so anytime y is 0, it makes the same slope all the way across, and it looks like 1. So if y is 0, I don't know anything about that. If y is 0, the slopes would be 0, so it can't be this. If y is 0, the slopes are x, so it can't be this, because this wants the slopes to be 1. If y is 0, the slopes are x, so it can't be that. If y is 0, every slope is 1. That's a very good possibility. And if y is 0, yeah, I don't know anything about this one except for when x is changing, the slope would change, and it can't be that. And when x is changing, the slope would change. So you can also try a few numbers. You can be like, okay, the slope field for y equals x. What that means is if x is the same number, x equals 3, 4, 5, 6, or something like that, those should all be the same, and that's not true. So it's got to be D. Okay? Okay, now you guys, this next question is actually a little bit different. Okay, check it out. It's showing me that, like, okay, these are the y equations, not dy dx. I mean, I can look at these and make them dy dx and look at slope fields, but these are the y equations. So we're kind of just trying to know, like, hey, what makes that? What makes that picture? You guys, I would like you to know what e to the x looks like and what ln of x looks like. All right, if you forget, so for part A, e to the x, well, e to the 0 is 1, and e to the 1 is e, so it goes like that. Okay, that's e to the x. E to the negative x. When I put a negative in, it rotates it on the x-axis. That's e to the negative x. A negative in front flips it upside down. So it's this graph, an A, but it's flipped upside down. That's e to the negative x. Okay? Let's see. I'll put D and E up here. ln and negative ln. Let me do regular ln first. You guys, there's two things I'll remember. The ln of 1 is 0. The ln of e is 1. So ln goes like that. And so negative ln would go like that. Okay? Now, which one does this most look like? I mean, I could say negative ln, except for that it does come over into this area. So it actually looks the most like b, e to the negative x. So that's kind of how we can do that, because if I pick a point, I can get a slope field equation going through there. All right? Okay, here comes the fun part, guys. We're going to learn something called Euler's method. Okay, I got to talk a little bit faster. Nah, we're okay. All right. There's a more precise method of graphing an approximate solution to a differential. Use Euler's method to construct a solution for a differential. Start at the point 0, 1. We have this chart, 0, 1, and use a step size of delta x is 0.1. All right, here's how this works. Okay, so guys, what we're doing is we're making an approximate, it's almost like the tangent lines. We're kind of going up by the tangent lines. Here's how this works. Okay, so first of all, wants me to start at 0.1 and use a step size of start at the point 0, 1 and use a step size of 0.1. Well, I can go and fill that in right now, because then my x is going to be 0.1, 0.2, 0.3. And we can kind of see it wants me to find the y value of 0.3 anyway, so I need to work my way through there. Okay, so I've got my x and y coordinate. Then right here we say, okay, well, what is dy dx, right? And we're finding the slope based on this equation. A lot of people like to just put this in here. So I know what's the slope at that point. Well, the slope is y, so the slope at that point is 1. Okay, now here's how this last part works, okay? You ever wonder why it's dy dx? Well, it kind of stands for delta y, delta x, like change in y, change in x. So think about this real quick. If dy dx, the derivative is the slope, okay? And we talked about separating like differentials, and I could bring the dx up here. So does it make sense that dy, or the change in y, would be the slope times the change in x? The change in y is the slope times the change in x. Because let's say I have a point right here, and I know what the slope is, all right? And if I go over x and up y, that's my slope, and that's my new point. It's just that dy dx is the slope, and so the change in y is the slope times the change in x, okay? So you go like this. So here we go, complete this chart. So now at this point, the change in y is the slope times the change in x, and that equals 0.1. And so that's my new y value, okay? Sorry, not my new y value, my new change in y value is what I meant. So y goes from 1 and adds 0.1, so it's now 1.1. And you might be like, well, if it's 1.1, then why is that just not 1.2, 1.3? So it's not, okay? Just check this out. Just keep, trust the process, guys. All right, so here's my next one. dy dx, now the derivative at that point, okay? So it doesn't want me to... Yeah, this graph is here so we can kind of look at what we're doing. I'll show you guys that in a minute. Okay, so the derivative at this point right here is y. So the derivative is 1.1. Now, the next change in y is the slope times 0.1. So you guys know what? 11 times 1 is 11. Move the decimal place over 2 times, so now it's 0.11. That's my new step. So 1.1 plus 0.11, it looks like it's 1.21. And now my slope is y, so my slope is 1.21, my dy dx. So the change in y is this new slope times the change in x. Okay, well that's 1, 2, 1 times 1 is 1, 2, 1, 1, 2, 3. Move the decimal place 2 times, it's 1.121. And so now I'm taking this and I'm adding 0.121. 1, 3, 3, 1. So I get 1, 3, 3, 1. Okay? All right, so I was able to fill out my chart. So I'm approximating this with, sort of like with slopes. It's called Euler's method. I'm approximating this, and y of 3, I get to approximately 1.331. Okay? And like on my graph over here, if you can see it, like, so like my first point is the point 0, 1. And then I go over by 0.1, and it goes to 1.1. And then I go over by 0.2, and it goes 1.21. Okay, and then I go over 0.3, and it's 1.331. All right, and you can kind of see how this like goes through there. Okay, this is called Euler's method. Now, let's solve this algebraically and fill in the actual values, okay? So I think we're going to like separate the differentials just to kind of see what this looks like. Cool? All right, so I'm going to go ahead and move the dx up here. I'm going to move so it says dy is y dx, and I'm going to move the y down here. So 1 over y dy equals dx. Okay, let's go ahead and integrate this. The integral of 1 over y is ln of y, and the integral of 1 is x plus a constant, okay? Then if I go e to every power, y is e to the x, and then this plus constant, but you guys remember how that's not plus a constant, it's e to the constant, and I can just make that a new constant right here. So y is a constant times e to the x. Now, you could have plugged in the point at any time, but we're starting at the point 0, 1. So x is 0, y is 1. Okay, so y is 1 when x is 0. So 1 equals c times 1, so the constant is just 1. So you guys, solving my differential just gave me e to the x. Okay, y is e to the x. So now I'm going to go to a calculator. And I'm just going to use, let's pull up a new tab here, Desmos Scientific. Okay, this will be easy enough. And I go like this, okay? E to the 1, right? And then I was going to do e to the x. Oh, sorry. E to the 0 is what I'm starting with. Shoot. Let's do a split screen here. Okay. There we go. Sorry, my bad. E to the 0 is 1. So that's my first point right here. 0, 1. Okay. E to the 0.1 is 1.105. Okay. E to the 0.2, e to the 0.2 is 1.221. And then if I do e to the 0.3, to the 0.3 is 1.349. Okay, so those are like my algebraic values there. And you can kind of compare that my approximation got me, kind of close. 1.331, 1.349. So semi-close, okay? All right, let's do one more Euler's method. Graph the points and see if you guys get the idea here. Okay, so this is having me start with 0 and 0.5. Okay. Let delta x be 0.2, which means I'm going to go to 0.2, 0.4, 0.6. So that's why it's having me solve for that. The differential equation is dy dx is x minus y. Now, this is an impossible differential equation to solve algebraically. That's why we have to do this. I can't separate the variables because it's not x times y, it's x minus y. So I can't move those over, okay? We're going to do 3 steps. We're going to graph as we go. So first step, 0.5. All right, now dy dx is x minus y. So let's fill this in as we go. 0 minus 0.5 is negative 0.5. So that's my slope right here. So it's like a negative half. It's like a slope like that. So the change in y is going to be my slope times my change in x, which was 0.2. And 0.5 times 0.2, okay, 5 times 2 is 10. Move the decimal over 2 times, so that's going to be negative 0.1. So that'll be 0.4. So that'll go to there, 2.4. Okay? Okay, dy dx is x minus y. 0.2 minus 0.4. So I fill this in by just doing what dy dx is. 0.2 minus 0.4 is negative 0.2. So my change in y is my slope times my change in x. 2 times 2 is 4. Move the decimal 2 times, so that's 0.04. Okay? And then I have to do, okay, what's 0.4 minus 0.04? 0.4 minus 0.04. 40 minus 4 is 36.36. Okay. Whew. All right. Little decimal-y stuff. So 0.4, 0.36. All right. Then my derivative is x minus y. So 0.4 minus 0.36. So that's 0.04. Oh, and this time it's actually positive. Okay. This time it's looking like it's actually positive. So delta y is going to be 0.04 times 0.2. Or difference is 8, and then I have to move the decimal 1, 2, 3 times. So it's 0.008, and then if I add that to y, 0.368, it will add it on there. So I got 0.368. Okay? So 0.6, 0.368, so like about right there. I like up a little bit, so it kind of went down and then up a little bit, I guess. All right? And that's how you do a Euler approximation. Very algebra heavy, a lot of times with little decimals and stuff like that. Okay, sketch a particular solution to passing through the point using the slope fields given. Do the two graphs coincide? So this is a slope field of y prime equals x minus y. And go ahead and look at that slope field. So if y prime is x minus y, there's my slope field. Okay? So it kind of looks like we're looking at the first quadrant here. Okay, so that kind of looks like the slope field that it's showing. X minus y. Okay, now looking at this slope field, passing through the point 0.5, look at what happens. Okay, so I'm going to draw this down. We're kind of following through here. Then we start to go up at the end. It kind of looks like that. I mean, I think so. All right. So hopefully you guys are okay with Euler's method and slope field, and we will tackle some more of these problems in class.